let's see. Let's go with finish up what we've been talking about on this semester. This is the last one before I go off to Europe. So I want to resume if people are interested in the fall. I get back in August. It's just informal, so we can do anything we want really. But I'll review what I'm going to tend to do with that at the end and see if people are really interested still. So we've got the nuts and bolts to put together a way of doing some kind of quantitative spectroscopy that we're going to try and infer plasma properties from. And I'm just going to take you through some of the language that people use in coronal physics. And that picture there is from an eclipse with various emission lines superimposed and highly processed, and then with the AAA data underneath it to show, you know, what we're talking about. This is the corona, as if you like. One of the characteristics I want to point out is at the very top of the sun, you have this dark region. So this is within the limb, and that's a coronal hole. And that's sort of the reason that's interesting is because it shows you that the lower bound, the boundary condition for the radiation underneath the corona is basically black. I mean, there's no radiation at UV wavelengths there, and EUV when we observe with things like AAA. And that's one of the simplifications of this thing. So here is just as an example, a spectrum, and here we've gone into EUV. You may understand now why we want to do that. There are many transitions of all these simpler ions, like the beryllium-like ion that we talked about, and boron, lithium, carbon, nitrogen, oxygen. They get more and more complicated. But what we see here is a typical spectrum of a region above the limb, and you can see that essentially the background radiation is almost zero, and which is what I just said, but it's superposed with all these bright emission lines on it. And this has been the subject of much research since Richard Towsey and other people flew these V2 rockets with instruments on them, showing that you had, UV and then far UV, EUV, and X-rays. And most of it consists of these emission lines, except when you get to very hot temperatures, in which case some of the radiation comes from the plasma itself, from the electrons interacting with each other. So we have Bremsstrahlung. So what can we do with this? I mean, we look at this, and there are patterns in there: magnesium 9, silicon 8. These are very strong lines in the spectrum that cause things like the thermosphere and ionosphere to exist. And then, so there's a whole host of these things, and a lot of the language in solar physics in the last few decades, in particular, starting with the OSO series of satellites in the 70s, the Skylab, and then SMM, and then we go into the 90s with things like SOHO, TRACE, and then of course SDO and all this stuff. And they're observing these things, and for instance, TRACE, I beg your pardon, SDO has a band around, say, 335, and this is just happens to coincide. This is a relatively quiet region, so you don't see the really hot stuff here. So, what are people trying to do with these things? And I'm going to try and take you through to show you more or less what the essence of what quantitative spectroscopy of the plasma does in this region. So what is this simplest model? It's basically that the densities are low enough and the plasma is hot enough, so it's pretty well ionized, and there are a whole bunch of ions all the way from, say, neutral hydrogen in a very small 10⁻⁶ kind of level, because it's fully ionized, because it's so hot. So you have a big tail on electron distribution, all the way through, I mean, to like iron, 10 times ionized iron, up to 1 million degrees. And then you get up to, like almost completely stripped iron by the time you're in flares. So that's typically what you're talking about. Because it's low density, that means that for each ion, imagine say an atom of iron with 10 electrons removed. Which are the eigenstates that are populated in this plasma? Well, they're almost always in the ground state of the ion. So what that means is that if you've got 10 electrons removed, almost all the iron will exist in a state where it's relatively decayed down to its own ground state of that ion, and then say one with iron with 9 electrons removed, which of course occupies the same volume as a plasma, because there's always a distribution of ions at a certain temperature. It's not that each ion picks out one temperature at all, anything like that, and we'll talk about this. But what it's basically doing is all the populations of all these atomic levels sit in the lowest levels of each ion. And that's because the Einstein A coefficients that we talked about are so fast that any excited states tend to drop down into these slots. And so it's like you know, if I were to use the hotel room analogy, then you know, all the people are in the ground floor. There's nobody occupying the first, say, 10 levels, and then there's an 11th level where you've ripped another electron off, and then everybody's in that hotel floor as well. So what we've got here is a special situation that occurs because of low densities, in which if we can keep track of the ion populations, we can kind of separate the calculation for the ion distributions, so ionization, recombination, and all that stuff, and we can within each ion then compute separately the bound states within that ion without worrying too much about bound states in the other ions except for the ground states. So this is a conceptual kind of thing that is an approximate kind of thing. I mean, if you think of what dielectronic recombination is, that's not quite right, because but it's a first order approximation to keep in mind here. The other aspect of this is that it seems that there's absolutely no photon scattering. The plasma is very low density, so therefore, you know, the integrated column of material never builds up enough to build a large optical depth. Unlike, say, Lyman alpha in the sun, H Lyman alpha, which through the chromosphere has an optical depth of, say, 10 to the 8 at the base and 10 to the minus whatever it is in the transition region, way above it, many scale heights above. So we're not dealing with photon scattering. What we essentially have then is a system in which all these internal degrees of freedom of the atom, which end up with radiation coming out of them, and we're measuring, and we saw in that spectrum, is the result of thermal electron impact and radiative decay. And I use the word thermal. Again, Tom at the beginning was asking how good is that, and we've got to remember what we mean by that is while it's just an approximation that we will use to try and get the right distribution of electron energies, which are able, like Einstein's photoelectric effect, to get over the threshold to excite these internal bound states. There is no detailed balance. So remember we talked about you know, the reverse ability of processes on microscopic scales as a result of the time symmetry in Newton's laws. So that is not the case. Instead, we have something that we call statistical equilibrium, and this is again another approximation. So this is all the approximations I'm essentially listing here for this thing. And we're going to get to things like emission measures shortly, so that you can appreciate where this comes from simply. So what we do is we imagine, we make these assumptions and we see what happens. And I'll show you exactly what happens with a variety of calculations compared with observations here. But this approximation says that if we write down, let's say, a continuum equation for the number density or the fluid density, say, mass density of the ion, partial dN by dt plus the divergence of that. That equals the sources minus the sinks. Now, so what we're talking about here is within a volume, imagine, putting a spherical volume, and you're looking at the rate of change of the population density inside that volume of a particular eigenstate. Remember, these are long-lived states compared with, any atomic time you want to think of, like the radius of the atom divided by the speed of the electrons or whatever. These are really static things compared with that. And so each one of these levels then, so we'd have a subscript I on that partial dN by dt and div, and we would say that's equal to the sources of that atomic level minus the sinks. And what are the sources and sinks? Well, if we have an atom embedded in this thing and it's in a ground state, then we want to know how the n equals 2 or 3 levels are populated. Then the electrons, those with enough energy, are going to produce a source of photons, a source of population of that level, n, and then it's going to decay very rapidly via some kind of electric dipole transition, or it's going to decay slowly via some other kind of transition, which, that's in the textbooks that I just pointed to. And what the assumption here is that those sources minus sinks are going on a particular time scale, such that that is a very rapid, compared with the fluid timescales or the kinetic timescales on the left. So what that means is that the sources, so that if there's an imbalance between the sources and the sinks, it very rapidly adjusts itself to balance the sources of the sinks. And so what that means is dN by dt plus div, we can effectively set to 0. That is the assumption. Okay? What that means is, and this is, if you look at, classic stellar atmospheres, this is part of the, equations that people would use, is to set the things to 0. And so what you end up with is the sources minus the sinks, and the sources depend on things like the collision rates, the decay rates, the recombination rates, the ionization rates, and we've talked about how to calculate those. And so you can put in a number, and typically in the corona, something like the corona is going to relax on a time scale. In the quiet corona, you may have the slowest thing that's going on the right-hand side is probably recombination, and that's going on a time scale of about 10 to the minus 11 times the, so it's going to take about a few hundred seconds. So we can only assume this thing is going to be working well on a time scale of a few. We better be aware that it could break down on time scales if we see changes that are much more rapid than that. Now, this has consequences. The sources and the sinks, remember, we have a thermal plasma by assumption. It has the impacts are by electrons only. And so these rate coefficients, the inelastic collisions go on at this time scale of seconds on, so NE times the, now we take the Boltzmann distribution and the cross section for the process, and we average over the entire vector velocity in the distribution. And what happens then is it must turn out to be only a function of the electron density times a function of temperature. That's all it can be. And you can see, imagine looking at the, just integrating up the Boltzmann distribution. If you integrate that over velocity, that's what those angle brackets mean, then it's got to be a function of temperature, okay? This means that things like ionization fractions are functions only of electron temperature. So we've already got a simplification here. Once we know the temperature now, we know the relative populations in principle by setting the Ni by dt on the left-hand side to 0. We balance the sources and sinks, and we end up with a distribution of number densities of atoms of ions in their ground states. The emergent radiation doesn't come from the ground states, it comes from higher energies. And so, but it is by the conservation of energy. If I just write down what the power radiated, if we do have an excited level J with an Einstein A coefficient of Ji. That's centimeters cubed minus 3 per second. And the dz is, you just integrate all those rates along the line of sight, and h nu is just the energy. So this is the intensity of the radiation. We divide by 4 pi to get this intensity. If we want the complete power, it's just h nu nj aja delta z, and that's in, for instance, ergs per square centimeters per second. Okay, so that is what we measure in the spectra from a given pixel. We integrate over the area of the sun with the pixel, and we get a number that's one of these spectra. And so when we look at that, we know that the inelastic collisions go as NE times a function of temperature, but for each NE, we've got a certain, and that's a plasma density now because it's fully ionized, we've got a certain number of, say, ion atoms. And so that population of ion atoms is also proportional to NE. So when we combine all this stuff, the emergent radiation varies as NE squared times a function of temperature times delta Z. All very straightforward. Okay, now I'm gonna tell you what I'm anticipating to talk about next fall. So what is this? This is a plot of, as a function of the density of the plasma, Ne, and we've got the corona on the left, and we've got the photosphere essentially on the right. And it's changing by, that's 12 orders of magnitude in electron density there. So it's deeper than the photosphere. But and of course, if we look at the corona, we've got the low, that's called a low density case. Low in the sense of the Einstein A coefficients are fast enough to everything to relax to the ground states of the ions, all the way to the right-hand side where we have the stellar interiors and also laboratory plasmas, where we have much higher densities. Okay, so and this is a figure from David Bates et al. Bates was part of the British Massey, Seaton, Bates, Kingston. There's a whole lot of people that work on plasma diagnostics here, and again, it's summarized in Cooper. So what we got here is this is the ratio of the number density and the ground state to the number density of ions. Okay, so then at some particular temperatures that are shown that. Okay, so what we're seeing here is on the left-hand side, we've got zero dependence on electron density, which is precisely what I pointed out here. The ionization fraction is linearly proportional to the electron density, but it's a function of temperature. Okay. The linear proportionality in NE of FTE, because I've written inelastic collisions there, the recombination rate varies as Ne, and the ionization rate varies as Ne. So those cancel out in this static equilibrium situation. As we start to increase, we end up. So let's just say that the coronal approximation then would be expected to sort of work for hydrogen. Remember, that's just a single electron system impacted by other electrons. Would work in regime like from anywhere from the base of that arrow to the left, say. I mean, within a factor of 2, you would get the right answer. So you think, well, the corona is mainly, you know, even the active corona maybe is 10 to the 10 at most, you know, 10 to the 9 maybe. So you'd think you're in pretty good shape, but this is hydrogen. In fact, that arrow should be moved to the left for more complicated ions. Now, as we get to a higher density, the two-body approximation is breaking down, and we have to balance the collisional ionization with collisional recombination. So it's a two-body and a three-body process. And you can see that on the right-hand side, the variation goes as 1 over the electron density. So we no longer have the coronal approximation. And in that arrow there, I've got something that I'm going to call collisional radiative. This is from Bates and people. There is a so-called model of these more dense plasmas. And basically the idea is that you relax the assumption that the atom decays very quickly. And so what you say is that, well, the levels within each ion are then getting closer and closer to being an LTE, because you've got a balance between collisions up and collisions down, or collisions in general, okay? So this is typically what people talk about. But and so I'm talking about the left-hand side today. The right-hand side of this figure is something I'm going to get to. But if you think about it in astronomy, if you've got an electron density of 10 to the 14 compared with 10 to the 8, that's 6 orders of magnitude larger. For an astrophysical plasma, they are often big structures. I mean, much bigger than in the laboratory. So instead of just doing collisional radiative, where that assumption is made, we also have to include the J terms. Remember, we had A, J, I plus B, J, I, J bar, and all that stuff, and even in the statistical equilibrium. So in astronomy, we tend to end up going all the way to include radiation in this thing. And in fact, you know, just in general, you should include that. It just happens that there is a collisional radiative model which you can read about, and there are things like people talk about ionizing plasmas and recombining plasmas. These are just eigenfunctions of the rate matrices. So you have a collision between one level and another, and you build a whole matrix of that thing, and you figure out what the eigenfunction and in time look like. And the first couple of ones look like ionization and recombination. So they're called ionizing plasmas and recombining plasmas. But that model is not terribly common in astrophysics because of this extra piece of information we have, which is that these plasmas are just big. Okay. Let's go down to the two-level system again. And again, this is for hydrogen for tutorial purposes. And as we said, essentially hydrogen it does only have radiative recombination, and we did that calculation, a handwritten calculation to figure out what that was. And as I said, it goes as like T to the minus a half, T to the minus 0.7, something that depends on the nature of the cross section. So what are we looking at here? Well, let's look at the dashed lines. That's the recombination rate at which, for a certain number of electrons, so we look at the lowest little triangle at the bottom, and you see that as the temperature increases, the recombination rate per electron drops with temperature. Okay, and that's the result we got by integrating up the photonization cross-section with a Planck function. This is very typical, and you can see that those dashed lines are all parallel. What are the different dashed lines? The different ions. So it's the same one electron system hitting a nucleus, a bare nucleus, and recombining. And those rates all follow each other in a certain pattern. So now we can see what I said earlier about statistical equilibrium. If we look at, say, the lower triangle again with H plus, and we imagine hitting that with an electron density of 10 to the 11 particles per cubic centimeter, because, you know, this is more a chromospheric ion, it's going to get very highly ionized, and recombination is going to be very, very small to hydrogen at coronal temperatures. So let's just say it's around 10 to the 4 Kelvin. Then we have, and the plasmas in that region have a density of around 10 to the 11 in the sun. So we take, that's 4 times 10 to the minus 13, multiplied by 10 to the 11, and we get 4 10 to the minus 2. So we get about a recombination rate of about 100 seconds, 10 to the 2 seconds, between 10 and 10 to the 2. And as we go to more highly charged ions, we get much larger recombination rates. That's because the Coulomb force is pulling the electrons in more strongly. But of course, as we go to higher ions, we're looking at less and less dense plasmas. So, for instance, something like carbon-6, which is in the middle here, this one, is going to have a recombination rate that's going to form around 10 to the 6 Kelvin. Okay, I just happen to know that. So in here, but we've got 10 to the 9 particles per cubic centimeter, or 10 to the 8 electrons. So again, we have about a factor of 10 less recombination rate than in a hydrogen case, simply because of the nature of the plasmas we look at in the sun. Those numbers will change dramatically if you have a different kind of star, for instance, or if temperature distributions are different. Okay, so what does this all mean? It means we've got a relaxation time. So if I were to release an atom and not heat, not give it any more energy, and just wait for it to recombine, it would take on the order of 100 seconds or so in the sun. So that's where that number came from. Now, if we look at the ionization curves, however, remember we calculated that classically, and we found out that it wasn't too bad, actually. And you can see this effect of the threshold. For recombination, there is no threshold, so there's just a Coulomb attraction. So what that means is that no matter if the electron energy is 0, it can't stay in that potential well too long before it gets recombining. But on the other hand, the ionization, there is a threshold, and for hydrogen it's 13.6 electron volts, and you know that it goes as the charge squared. So for sulfur 16, that's hydrogen-like sulfur, the recombination or the ionization is very, very slow. That's over here, because the energy is so high. So there are very, very few electrons above that threshold. So what we've got is a situation in which at low temperatures, ions tend to pile up in the ground state, and as you get to higher temperatures, they get more and more and more ionized because these rates are going up. And the place where this balances is given by this dotted curve here. So that's the place at which you switch from hydrogen plus to H. So in equilibrium, the intersection of that dotted line would be an equal population of neutral hydrogen and protons. But you can see this is changing interestingly with temperature. And in fact, you can show that the temperature at which ionization is equal to the recombination, it scales to something like this. Okay. And this is just showing you a way to remember it. It's 11,000 Kelvin, corresponds to 1 eV. And so, again, these are just two-body processes, okay? This is a guide, so it tells you roughly, if you imagine I being R, if we're too far from this temperature, either too low or too high, then we don't have to worry about this particular ion, because imagine being at 10 to the 6 Kelvin, hydrogen is fully ionized, but now look at the amount of, it's so far above the temperature at which these two are equal that hydrogen is completely ionized. So it's 10 to the minus 6 or something of population. This basically tells you the temperature at which you have to worry about where the ions are in temperature space. And of course, this is this plot that confused Tom, but we talked about. But again, this is just the ionization equilibrium from the two-body approximation, but including those things that we talked about from the internal degrees of freedom as a result of dielectronic recombination. And again, you can find out where, by looking at these plots, you can see where the noble gases are. So that's the helium, that big plateau on the left there, of where it's very resiliently being not ionized for a large temperature range, all the way up to about 3 10 to the 5 Kelvin, 10 to the 4 Kelvin. And then there's another one here, which is neon-like, okay? So these are the closed shells. So they're very resilient. So you can then say, well, the neighboring one has to be, if that's neon-like, the neighboring one to the left has to be lithium-like. And the one to the left of that has to be beryllium light. So you can understand these things very, very easily using this little mnemonic here. Let's move from that to the internal degrees of freedom within each ion. And let's do what I said, which is let's just disconnect the ionization problem from it completely on the basis of assuming that those levels live a long time. The level number 1 lives a long time, but the levels number 2 and 3 don't live very long. They got very little population in them. And the reason they have very little population in them is because of the assumption of statistical equilibrium at low densities. So for instance, the population of level 3, which is this one up here, what do we have? We have collisions up, which is here, from this highly populated ground level, and then we have radiation down in transitions 3 and 1 and 3 and 2. Okay, so that is the statistical equilibrium equation. And now this is going to relax. If that's an electric dipole transition, we go from collision rates, which are on the order of, we said it's going to take about 100 seconds for recombination. If the temperature is very high, then the ionization rate goes much faster, et cetera, et cetera. But C13 is on the order of about something like a few times this recombination rate, just from the fact that we've, well, more like the ionization rate, but increasing because the energy is not as big as the ionization rate, so we have more electrons to excite them. So what we've got here is a balance between collisions up and radiation down. That's basically it. Of course, we have collisions down, which we've missed here because by definition, that's our assumption. And then more generally, we have something that looks like this if you've got a lot of levels. And this is what the coronal people sort of use. This is what's used in Chianti, for instance, this kind of thing. So instead of 3 levels, you have as many levels as they put in, like 90 levels for carbon 3 or something, and you just solve this set of equations here, and you end up with a distribution of populations. But remember, the A's correspond to the spontaneous emission of a photon. So that is the source of the radiation we're observing, okay? So now let's put it together and get to the point where the intensity I sub I here on the right-hand side, that's just the statement I had earlier, which is that the intensity, conservation of radiative energy here, if we have a total number of photons coming out with a population of N upper, the transition I, then that thing turns out to be ergs per square centimeter per second per steradian, which is what we're measuring, right? So we want to relate that to properties of the plasma. The left-hand side, epsilon, the top one, is just a statement that the energy is distributed also in frequency. But notice that on the right-hand side, I've integrated that out because the integral of phi nu is 1 by definition here. In other words, we're conserving the energy radiated into 4 pi steradians. The plasma is going to determine the frequency distribution by its velocities of those ions as it's emitting. And so we end up with an equation on the top right-hand side. Let's go down to the next second line. And we assume again that the Einstein coefficients are much bigger than the collisions. This is not true in anything other than the coronal approximation here. And so what we end up with is an expression that looks like the one under the 2-level atomic ion there, this expression. And this collision rate here is so small compared with A, we can just trash it because of that inequality that we've assumed. So we end up with replacing N upper, A upper level here with just the collision rate up. So all that's going on, in fact, is, well, we've got this ground level, we knock an electron up into this state, and then it's radiated away. It's not collisionally de-excited. And so what does all this amount to? Well, this looks kind of convoluted, and it's just a factorization into things that are easy to understand. So we got the lower level population of the ion here, say, and a collision rate up here. Now, I want to expand that in terms of, well, what is the population at that low level compared with the ion? That number would be 1 for, essentially, for a hydrogen-like ion. That would mean the lower level is electrons are impacting and exciting the transition up to, say, Lyman alpha, and then it's radiating away. So that number is going to be like the number density in the n equals 1 level, and that's the number density in the whole hydrogen ion, and that's going to be the number density of the ion. So that number is 1, for instance, or it's some very weak function of temperature that's at most 1, and at least something like a half or a third or something. This ion over NL, this is the number of ions per number of total ions in that element. So that's from the ionization equilibrium. That's all that is. And that's a function of temperature. And then we have the abundance, and then we have, for an astrophysical ionized plasma, we have 0.8 for the ratio of the number of total hydrogen nuclei compared with electrons. So if we factor that out, then what we've got here effectively is just we go from this equation here down to this one, factoring in all these, and we end up with something that looks like this. And what that says is that, well, we've got the brightness of the EUV corona is going to be integrated along the line of sight, and we go all the way down into the photosphere where the brightness is 0, and so we just integrate all the way from, because the temperature is so low, and then we integrate from the surface towards us, and we get this thing that looks like NE squared GITE. Okay. Now we just want to define something that's a function of the sun's plasma and not of each atom, a specific atomic system. So what we do is we make the transformation such that NE squared G dz, that's the integral we're doing, is equal to an integral over temperature. And it has a source term in it called psi, and we're integrating over temperature. Okay, this may look peculiar, but it's essentially everything on the right-hand side is now solar except for the GI. And so we have essentially got a distribution here. And so what we're doing is we're integrating over the areas, the shaded areas of the emission lines here, and each one of those has its own G of T, and we're trying to figure out what psi of T is, okay? And here's one example, and I'll tell you what this means in a moment. Often it's written as psi of T E dt by dH is equal to NE squared, but it's not a differential, it's a distribution function, and it has a particular shape. This is very characteristic of what we find. And this, for some reason, the sun wants to make plasmas that have this distribution here. And this was sort of the result of Potash, Jordan, Dupre, a lot of people, Athay in the 60s, 70s, 80s. This has been derived forever. And this thing is called various things, one of them being a differential emission measure. Okay? All right, so what is this thing actually physically? Well, imagine looking through the plasmas at the top there, and either we're looking on the disk, in which case the intensity is 0, and then you integrate through the corona and it just adds up and up and up. Or you're looking into space behind it, and so you have the same thing. Imagine then the temperature varying along this line of sight quantity called S, and imagine drawing the temperature distribution. It could be anything. I've just drawn a smooth wiggly thing there. And now what we're doing is we look at how much stuff there is between T and T plus dt, and the stuff, and I've plotted the temperature there. So we know that between T and D plus, in that range of dt, we've got a little ds1 there on the left-hand side, at which the electron density is known to be this, or at least if we had a model, for instance, from Matthias, you have that. Okay, now we go along again, and it's not in the temperature range, and we find another one. Oh yeah, we have to add this one as well. So what we do is, this psi of t dt is a distribution function describing the product of n squared, or the integral of n squared ds along the line of sight. That's just what you get out of this thing, okay? A lot of people get confused as to what this thing is and play games with all kinds of formalisms in which you assume it is a smooth function. You assume it's, for instance, a monotonic function sometimes, and they play algebraic games of this thing. But the fact is that we always end up with something that looks sort of like this. And this is in logarithmic temperature. So it's not dt, but it's d log t here. And that curve, the right-hand side, is pretty well understood in terms of an energy equation that in the corona, which is dominated by heat conduction. Namely, you set the heat conduction divergence to 0 because it dominates. There's nothing to compete with it. The radiative losses in the corona are very small. And then you end up with an assumption of, say, constant pressure through the corona because it's so hot and the scale height is very large. Then you end up with a curve that can match that. The problem is that the lower part with 5.2 and below is actually still not understood. And I would say it's not understood at all at this point. But some people would disagree. I think they haven't looked at data that I have. So anyway, so that's what this thing means. And so what do we actually do with this thing? Okay, well, we write down a set of line intensities in terms of, and I'm just going to make it easier to think in terms of a matrix equation. So you discretize this thing in temperature. You have a discrete set of i's here, right? And you want to solve for this thing as a function of temperature. That's the goal here. Now, it should be obvious to many people that this is only possible if I multiply by, say it's a square matrix, I multiply by g ij to the -1 on both sides. So I'm basically got psi equals the inverse matrix times I. The inverse matrix has to be well conditioned in order for it to reveal a unique answer. In other words, it can't have eigenvalues that are too small. Unfortunately, that's not the case. And it's easy to understand why. Those GT functions are slight modifications of these kind of curves here. What is this? This is ionization equilibrium. Look how broad these things are. Each one of these spans about 0.2 to 0.3 in log. So when people say a line is formed at 10 to the 6 Kelvin, that's just the 0th approximation for the kind of peak value there. But you've got very blunt instruments here. Now each one of these is a g of t function, and you imagine stacking those up as a function of temperature in that matrix G, then you can see that these have a lot of overlap. That means there's a hell of a lot of redundancy in a set of data. If I were to observe lines of iron 7, 8, 9, and 10, you'd say, well, we got more or less the whole quiet corona covered. Well, that's true, but you're integrating over so much, you couldn't resolve anything below, whatever the width of those things is without some clever tricks. But also, look, there's two kinds of calculations there. There's three kinds of calculations from Chianti. There are two of them. They differ. And so we've got systematic problems as well here. One of the good things about the emission measured approach is that you can integrate over, you can build what's called a radiative loss function. It's just simply the sum of all those, all the radiation coming out of a plasma, and calculate it as a function of temperature, because remember, all the physics here is a function of temperature. There's no density term involved here, except as a linear multiplier or a squared multiplier. So what is this? This is showing you a constant the right-hand side is constant pressure, and the left-hand side is constant number of electron density. And what I've shown you here is all those G of T functions which come from this, they all live, and in fact, you know, I put iron 8 to 13 up here. We've got all, and the contributions to these things are mostly dominated by these trace elements here. That's because at low temperatures, hydrogen is not ionized, so you can get a lot of power out of hydrogen radiation. It's not fully ionized. By the time you get out here to about 10 to the 5 Kelvin, you don't have any hydrogen left. There's nothing left to radiate in those ions. And helium is very difficult to ionize and very difficult to excite because it's only got delta N equals 1 transitions. So all you've got left are all these trace elements. And they're low abundance relative to hydrogen and helium. So the sun is a really poor radiator above around 10 to the 5 Kelvin. That is why I said you can use a constant conductive flux in the energy equation, because you multiply this by electron density squared, you get the radiative loss, energy loss rate due to radiation from the corona. At constant pressure, it looks even worse. And of course, the sun is almost at constant pressure. So you could vary from region to region, but the pressures are going to change, according to the boundary conditions underneath and the heating, all this stuff that we want to know. But the corona is a very poor radiator. For instance, if we look at 10 to the 6 Kelvin at constant pressure, it's 3 and 4 orders of magnitude smaller than hydrogen. So that's a useful thing to have learned from this. And you can see the relationship of this thing. If I now just were to put a path length on that bottom, that should be seconds to the -1, then this is the loss rate in the energy equation. But if we multiply it by a path length, dz, then we end up with the intensity of all the radiation coming out from the lines. So, this is a pretty useful thing to have. And you can see now that if I've got NE squared dz written in terms of the emission measure, that I can take the emission measure and figure these things out. So you can test the energy equation using this thing. Okay. Here are just some nice data showing you that there was an eclipse in 1970, and this bunch of maniacs, including my advisor and all kinds of interesting people from all over the place, Leo Goldberg, Garton is a famous laboratory physicist, etc. What they did was they shot a rocket across the path of the moon's shadow to get some spectra. And I just wanted to show you, because it's so beautiful, I think, that when you don't have the photosphere, you can see all these lines all the way out to, that's 2000 angstrom. And here we've got a line of iron 12 at 2000 angstrom, 2100, nickel 14. These are coronal emission lines. These are lithium-like ions of carbon. So this is sort of showing you what I just told you, which is there are very few coronal radiators here, and they're quite weak. The really strong ones are in the transition region. And the reason for that is very simple. It's because of this. You have a huge radiative loss rate there. And so a lot of people have studied the transition region ad nauseam. And so here's an example at the top of oxygen 5 and magnesium 10. And what people do is take these spectra, analyze them to death, and you end up with something that, by integrating over these things, again, you end up doing something, and here's the intensity, so we just can derive an emission measure distribution from these things. It turns out to be mathematically equivalent, but a different picture. The other thing we might try and do is to take two different lines with different GT functions and get the ratio of them as a function of temperature. Those are a function of temperature, each one of them. So if we then divide one intensity by the other, we might be able to derive a temperature from it. And that's what these guys did, okay? So this looks like a wonderful, consistent observed ratio, error bars, everything from these kind of spectra, et cetera, et cetera. But remember, behind these things, we've got a strong overlap in the GT functions. But let's just take a quicker look at that. But we've got the temperature nailed down to 1 part in almost 10 to the 3, 10 to the 6 plus, or the logarithmic temperature, plus or minus 0.01. That's absurd. That doesn't make any sense to me, because the width of these things is so great. What am I talking about? Well, instead of deriving an emission measure, what they did was they replaced the emission measure distribution with a delta function, and then basically computed the amount of emission for that delta function as a function of temperature. So that on the bottom thing is psi, which is equal to delta of T minus T plotted here. And so you end up asking the question, do I get a consistent temperature compatible with all those lines? And I think, the answer is in the eye of the beholder. This looks pretty impressive, right? You've got a very small collection around 10 to the 6 Kelvin. What that means is that I can represent all the emission from whatever this off limb, and this is quite high off the limb, with one temperature. So you've done equivalently to the emission measure distribution. You've just solved for the signal temperature that would represent those. But I don't know how to interpret this. Given the nature of those distribution functions. Here's an example of 2 lines which are sensitive to temperature. Okay. And it happens to be, I think it's beryllium-like again. It's the same old story, but this is the ratio of the 2s3p to 2s2p lines. So this is a big jump in temperature, which is why it's sensitive to temperature, this line ratio. Okay, so that can be done. We've also got coronal abundances to 3 significant figures, which is somewhat bothersome for me. If we have coronal line emission like we did at the beginning from above the limb during eclipse, say, then this problem is going to not fit very nicely into the differential emission measure. And that's because the G of T functions, the electrons, the basic assumption is only electrons is not true, because here we have, and I've got a plot here on the right of say, ion 13, very familiar to those of us. These are comp lines at 10747. But many of these ions in the 3rd row of the periodic table, this is a silicon-like ion, has a little bit of ground state splitting. So that this is because you've got a triplet P ground state, and the EUV transitions are up here. So everything's hunky-dory here because there's very little radiation coming from the sun at 20 nanometers. However, these are in the infrared, 1 micron, both of these lines, and I've blown them up here. But 1 micron, the sun is one hell of a powerhouse. It's got a lot of radiation coming out of it. And so we can't ignore the BJ terms here. Even though these are forbidden, electric dipole forbidden by definition, because there's a transition between states of the same parity. So the next higher order operator that comes in is magnetic dipole, and then electric quadrupole. But the strong photospheric radiation from the sun influences these lower levels, but not these EUV levels, okay? So while Chianti and stuff can do this, can do these levels, it can't do the ones on the right-hand side. Furthermore, the radiation emitted by these things carries an imprint of the anisotropy modified by the coronal magnetic field. This is what COMP measures, okay? It's not compatible with the coronal approximation. That's why we had to, Roberto basically wrote, and I helped him write this code to solve for the actual problem here with the incident radiation on these things. This is not the Hanley effect. The Hanley effect is for the cause of very strong lines, but it's in what we call a strong field limit of a Hanley effect. Oddly enough, the magnetic field in the corona turns out to be very, very strong. In other words, for these transitions, in other words, the splitting between the levels by the magnetic field is sufficient to destroy any kind of correlations in the wave function of the atom that would otherwise be modified by the magnetic field. Okay. If we have finite densities, we're not going to trash this. The coronal approximation is this one. If we have finite temperatures, we have to include finite densities. We have to include the collisional de-excitation rates. And so we end up with a different expression here. And so you'd end up with this thing now is, apart from this CLUL term, so that's a collisional de-excitation rate, that depends on density. We now have a G of T function that depends not just on T, but G, T, and N. So we could, in principle, try and solve for a distribution of N and T, but of course, you can see you pretty much run out of information because you've got a two-dimensional function you're trying to solve for from a 1D set of emission lines that have a lot of overlap with them. So this is a game of losing strategy here. But it's interesting, the coronal limit is NE squared. And if we go to high energies here, this then dominates this one. And so one term of the electrons drops out, and it varies as the electron density. So you've got a potential of measuring a density in the corona if you want, and this is just an example. This happens to be sulfur 4, which is that's not boron, it's aluminium-like, which is the same as boron. It has low-lying metastable levels with small a's and big c's, so it has these kind of transitions. And you can see that in something like, the solar transition region, this could be used to measure the electron density if you were to consider it by looking at the ratio. But again, I think you can see this is an inverse problem that's L-posed, et cetera, et cetera. And nevertheless, we have the current understanding from many people that are willing to make all these assumptions. We can derive all these quantities. Furthermore, we can get plasma beta if we extrapolate the magnetic field, etc. So, but this is the framework upon which much coronal physics is built. But if you're worried about any of this, if it seems a bit too good to be true, then I think you're understanding a bit more about what's going on here. What to make of all this? Well, here are the assumptions that we've made. And if we look at this one, the first 4 points are assumptions. And now we have this point. It's uniformly, all the radiation comes out to 4 pi steradians because there's no anisotropy. That's not necessarily true, especially if we have an optical depth that might be 0.1. You think, oh, it's optically thin, it's going to radiate isotropically. You've got to be very careful here. And there's quite a lot of evidence in papers I've published showing that a lot of the lines in the UV and EUV region, which you thought could be optically thin, are actually scattering. And so if you have a pair of lines whose ratio should be 2 to 1, sometimes you measure 1.5 to 1 or some other number. And people puzzle about this, but really it's got to do with the fact that you're not scattering in uniformly into 4 pi steradians. We have low density approximations. We measure line profiles that are not thermal. That means, in every part of the outer atmosphere of the sun, there's some component of fluid motions that we don't understand. Remember, we had dN by dt plus div of NV. Well, if you've got motions on small scales that are unresolved, but when we have a div of NV term in the statistical equilibrium, which we're not addressing, we really have to sort of think, well, maybe we're throwing something out with the bathwater here. We have L-posed problems, and we have extension to lines near the peak of the solar flux, which is not completely straightforward. That's what I just mentioned with the infrared and optical transitions. And yet we have this consensus within the community that we know pretty much a lot. But it's all based on this framework. Make your own mind up. This is why I've given up doing UV spectroscopy for me. I knew too much about it, and I said no. I also had some great advice from people like Tom, Andy Skumanich, painful advice early on, Art Hunhausen, to say, you know, look, you got to do something more important than this, which is why I've given up on it. But that's my choice. So to come in the fall, if you're interested, will be extension to the collisional radiative regime, the laboratory one, LTE and non-LTE as well, and that's it.
Okay, thank you.
I hope that was clear. Did you find the things clear?
I had one question. A few slides back, you showed the different G functions and different Chianti versions having slightly different results.
Yeah.
I was wondering, I mean, what are the main uncertainties there? I mean, I think, yeah, this one, which causes these differences. Is it atomic physics not well enough known, or just that we have to limit the amount of processes they consider in these calculations?
It's mostly the cross sections for things like ionization and recombination are computed using certain kinds of approximations and semi-empirical fits. We don't have all the cross sections at every energy for every ion. That's being filled in actually by these ion traps, where you put a few ions in a very, very low density environment, trap it with a magnetic field, keep it spinning, and you just observe the faint radiation. And so dielectronic recombination, you can remember that plot I showed you of the agreement between the resonances and the actual, that kind of thing is incredibly important for us to have confidence in what these things look like, right? But they're not based, they're based on a few spot measurements still, and not hardcore measurements of cross sections. It's incredibly timely. It's hard to get. I mean, imagine working with sulfur in the lab. I mean, that's really nasty, sticky stuff, right? I mean, you know, and so you make a lab, doing a lab experiment. It can be very elaborate, but they are being done, but it's not. It has been a funded thing from things like the NSF and other funding agencies abroad. But I got to say that these changes that you see here are mostly to do with those coefficients, with radiative and dielectronic recombination and collisional ionization, collisional excitation followed by ionization, autoionization. All these things go into these calculations. So I find it sobering. So if I did a calculation with one set of those curves and then tried to invert them using the other set of the curves, it's not good. So what does it mean? To me, it means that what you should be doing probably is to take a numerical experiment like you're doing with Muram and then synthesize these things and just see what's coming out. I don't see the inverse strategies. They have not informed us about heating in the corona very much at all, aside from just integrating over the total radiative power coming out of it and some of the velocities, so you get enthalpy fluxes and stuff like this. But I don't see a lot of use in deriving temperatures of plasmas and densities of plasmas when essentially you have such a huge null space that you can't probe with these kind of diagnostics, that you don't know what you're doing. And this is where I've differed from many of my colleagues in spectroscopy in astrophysics. And it's I think my points are valid, their points are valid, except that they can't go back. The worst thing about these kind of diagnostics is you can't actually prove that they work with a forward and inverse calculation. All you can show is consistency. And what does something like this kind of consistency really mean? I mean, this one. What does that mean? I don't know what that means. So I probed it with a paper many years ago where I just replaced the delta function with a Gaussian and asked the question, how wide would I have to make that Gaussian to be in disagreement with this result? And that answer was about plus or minus 0.15 in the log, so a factor of 2 in temperature. And because things like losses in the conduction, electron heat conduction equation of Spitzer, that goes as T to the 7/2. So you got no information on the from a measurement of the temperature on the energy associated with that. I just think, you know, we got better things to do. I personally would not build a UV spectrometer to observe the corona anymore unless I had a very, very good reason. So I'm not optimistic for Muse. I think that's just going to generate a lot of papers, and it will generate a lot of papers. Anybody?
Yeah, Phil, I just want to make sure I understand a certain point. You were saying that the line ratio techniques for getting at temperature can't be accurate because ultimately the GIJ matrix is ill-conditioned and there's no getting around that. Is that correct statement?
It's that compounded with the fact that we have those systematic sources of uncertainty, such that, for instance, we may or may not have a reason to choose a G of T function from any one of these 3 calculations.
Okay, so you're saying the different curves here are yet another problem, that the atomic data
Yes.
is
Yeah.
not known well enough for.
Yeah.
Okay.
The
Thank
other
you.
uncertainty is also the abundance, right? The
Yeah.
between photospheric and coronal abundances, these also change quite a bit, and depending on which evolutionary state an active region is in, it might be more photospheric, more coronal.
Yeah. So I hope that was useful. I want to thank everybody for tuning in, and, you know, please do let me know. If I don't hear from anybody, then I'll consider that my job is done and won't bother in the fall. So, but and I might offer something else in the fall. I'm not sure what yet, but because I think I want to share with people, especially the young folks, and of course people interested like Tom with an open mind, and Matthias. You know, this is just such a pleasure for me to, you know, offer up some, you know, objective, subjective mix of experience. And if that's useful in the fall, then please do ping me an email or something and let me know.
Bill, are these slides available online somewhere?
Yeah. If you go to the meeting, the meeting Google meeting, then I will put in, as I edit these things and improve them. I will make sure that's up to date by next week. And also, you know, we have recordings of these, thanks mostly to Ben and to Andrew and to Joan. So, yeah.
Oh, got it. Thank you, Daniela.
I couldn't find him on YouTube. Thanks again, Ben, for being such a stalwart and helping out with this.
Bill, thank you very much.